Okay guys, this is Mr. Galoy again. Hey, we're on part 2 of these notes. Again, these are notes on constant velocity motion. Let's kind of, we got through the first 2 pages, so let's kind of just recap what we did. We talked a little bit about Galileo. Galileo was the guy really that kind of discovered some of the equations and graphs of linear motion. Linear motion then represents objects that can stay at one speed. That would be constant velocity, maybe like a car that's traveling with its cruise control. It could be an object accelerating. It could be getting faster, getting slower. We're going to discuss acceleration in the next unit. This unit we're just talking about constant velocity. So a lot of this stuff was discovered by Galileo. So we really start off with a graph called the position time graph. That position time graph tells us positions or locations of different objects. We have a reference point, which on a graph is our origin. It's where the object or objects are starting. Could be somebody's house or a starting line, etc. on a race. And we talk about then that objects move through time. Final time minus an initial time is a delta time or a change of time. And we've also talked about how position can change. Final position minus an initial position represents then a delta x. X is the symbol for position. And a change of position then is called the displacement for the object. It's a very, very, very important word. Okay? Now let's go on to page 2 here. I've got this kind of tape here, and I'm just taping my notes down as I talk. Well, the important thing then of the graph is that if we have a line here, we have a lines in when objects move at constant velocity. When we have a line here, it means that we can get the slope and we can get this constant velocity equation. And we have the general nature of this equation then is the final position equals to the slope or the velocity times t plus the initial position. We can bring this to the other side, and xf minus xi represents displacement. So we have delta x equals vt. Now, we can show more than one object on a graph. In this case, we've got 2 runners, and we talked about that a little bit. Now, that really sets the stage for page 3. Okay? I'm going to tape mine down a little bit and then scroll back up. Now, we don't always have objects starting at the origin. We could have an object that starts in front of a reference point. How would we show that on the graph? Well, if an object is not starting at the reference point, then this intercept's not going to be at the origin. So we could have an object start in front of a reference point, or in front of the origin, or behind the origin. And so this could be a positive number, or it could even be a negative number. Now, so how would we write that equation then? Well, remember we have x sub f, final position, equals v sub t plus x sub I, where x sub I represents that initial position. Well, we'll keep this as a variable. The velocity then represents the slope. So let's put in our points here. We've got 10, 100, and we've got 0, 50. So our slope then would be 100 minus 50, okay, over 10 minus 0. So that'd be 50 over 10, or a slope then of 5. In this case, it'd be meters per second, times t. We'll leave t as a variable because that value can change. And our x sub I then represents our head start, or plus 50 meters. Okay, so that would represent the equation of a runner doing that. So maybe we want to know where the runner is at 6 seconds. Well, we know it's going to be around 80, but let's again use the equation. So we would take 5 times 6, that's 30 meters, plus 50, or that's your 80. and that confirms what we see on the graph. Generally, you can read things off graphs. The equations are much more accurate if we can do it that way. Now, let's take a look at this graph. It looks pretty complicated, and it really actually is. We've got two runners, and we've got runner A and runner B, and we've got some questions we'd like to ask about these two runners. Now, we always kind of start off with then writing the equation. So let's take a look at A. So we're going to have x sub f equals vt plus x sub I. Okay, well, let's take a look at runner A here. Runner A is not starting at the reference point. Runner A has a 30-meter head start. So we'll have to put that into our equation. Let's get our two coordinate points here, 15, 60. And then we have 0, 30. Okay, so x sub f, we'll keep that as a variable. V is the slope. So, okay guys, my batteries had run out, but I just switched them out, so I'm not sure how much of that last part you heard. Okay, we had these two runners, A and B. We want to start off with the equation. So we want to write x sub f equals the slope. Well, the slope then would be 60 minus 30 over 15 minus 0. So that's going to be 30 over 15. Or that's really a slope of 2 meters per second times t plus x sub I. Well, the x sub I represents the head start, and that's going to be 30 meters. Okay, so that would represent A. Let's maybe change our colors and maybe do B. Again, we have x sub f equals vt plus x sub I. X sub f, we'll leave that as a variable. Well, now we need the slope here. So we have 15, 100. 0, 0. So our slope would be 100 over 15. Okay, do your division there. That's going to be 6.67 meters per second plus 0 meters because B has no head start. So those are two equations. And again, those are powerful. Do a lot of stuff with these equations. So it says describe the motion of the runners. Well, runner B is running faster, right? Runner B has a higher slope. We can see that from the graph. Runner A is running slower. Runner A, though, has a head start. So this intersection point is pretty important here. It looks like it occurs between 6 and 7 seconds. What exactly is happening there? Well, in fact, one of the questions, what is happening at the intersection? It's kind of towards the bottom. Well, up to this point in time, who's winning the race? Well, runner A is winning, right? Runner A is at a farther place or a further position from this origin or reference point. After this intersection point, runner A is now behind. Runner B is leading. So, up to this intersection point, A's winning. Then after it, B's winning. So that intersection point, what exactly does that mean? Well, that means that's where the runners are at the same position, right? Runners are at the same position. They're actually, you could say runner A is getting passed by runner B at that point. So some of the questions we've already answered. Who's running faster? Let me maybe zoom in here. So who's running faster? Well, B is running faster. Is B always running faster? Yes. So B's actually running faster here because B has a larger slope. But B's actually behind. Does that kind of make sense? So an object could be going faster, but yet not be in front of the other object. So B's running faster. How do we know? Larger slope. Do any runners have a head start? Yes. runner A does, right? How much? Well, 30 meters. Do velocities change? No. B always has a velocity of 6.67. A always has a velocity of 2. These slopes don't change. These runners are staying at their respective velocities. It's like these runners have a cruise control on. Okay, they're not getting faster, they're not getting slower, they're just staying at their speeds. So do velocities change? No. Is runner B always running faster? Yes, because runner B always has a larger slope than A. Now, that's a really critical idea. An object can be kind of behind something else, but be going faster. Think of maybe you driving your car on K10. You know, there might be a car behind you that will eventually pass you. That car behind you, you know, is traveling faster. But you're still winning, you might say, on K10, at least till that car passes you. So who wins the race? Well, we have to kind of define, you know, what the race is. If we say the race is, you know, who gets further in 15 seconds, then, you know, B gets further, right? B gets to 100 meters, while A, you know, gets to 2 times 15 is 30 plus 30 is 60 meters. So we kind of have to know who or what really the race is defined as. You know, if the race is to 40 meters, you know, runner A gets there first, even though B's traveling faster. So who wins the race? Well, it depends on the length of the race, right? You know, if we say the race ends in 15 seconds, you know, whoever is furthest in 15 seconds, then B wins the race, right? By how far does B, you know, last question here we have, how far does the winner win? Well, B is at 100 meters at 15 seconds. A, we said, was at 60 meters. So we could subtract those two, 40 meters. So we can say then that runner B is 40 meters ahead of runner A at 15 seconds. Okay, so let's kind of, you got that? That's a pretty long page, but it's a pretty important page. We've got to, you know, you've got to be able to look, you know, you've got to be able to look at objects and compare what they're doing on a position time graph, all right? So let's maybe kind of look at page 4 real quick. And let's just maybe talk a little bit about this page. I think this page will go a little quicker here. Sometimes our position time graphs get a little more complicated. And let's kind of go up here to the top, this one. So let's say we have a graph that kind of looks like this. You know, what exactly does it mean? Well, the object's at 5 meters and is coming back to the reference point. So in this case, the object is going back towards the origin. Okay, let's write our equation down. Okay, x sub f, that stays as a variable. That equals to our slope. Okay, so we have 4, 0, and we have 0, 5. Oops, I'm not writing that very clear, sorry. So what's our slope then? 5 minus 0 over 0 minus 4. So that represents a negative 1.25 meters per second times t plus 5 meters, because that's our initial starting point. Does that kind of make sense? Let me scroll over here so you can see. See, we get a negative slope. See, you know that's a negative slope, right? It's a negative diagonal. Well, what does that mean for the object? The object is traveling back towards the starting point, or back towards the origin. Okay? Negative slope, all right? Now, again, we can use this equation. So we could say, well, where's the object at 2 seconds? Well, we can put 2 in there, right? negative 1.25 times 2. Well, that represents negative 2.5 meters plus 5. So at 2 seconds, the runner's 2.5 meters away from the starting point. Now, take a look at this graph. This is kind of an interesting graph. We have velocity here, and then we have this horizontal line. What would that imply then for the object? Well, the object is starting at the reference point. The object then moves 3 meters in 2 seconds. Then the object stays at 3 meters. So this represents then motion away from a reference point. And then the horizontal would be then an object then that's not moving. So the object's staying at that position, but the object's not moving. In physics terms, or physics lingo, we say the object's at rest. All right? So whenever you see a horizontal line here, that slope, right, is 0 meters per second. A slope of a horizontal. That means there's no motion, right? So maybe it's a stop sign and the object is stopped for a little bit, or maybe a stoplight. Okay, so we have motion away and then stopped. Now, what about this next one? This is pretty interesting, right? This would be motion away, then the object stops for a second, and then the object comes back. Okay? So, the object moves 3 meters away from the reference point. Then the object stops at 3 meters for 1 second, and then the object comes back. Now, there's a couple of words here I want to talk a little bit more about because they're very important. Distance versus displacement. Now, this may seem a little confusing at first. Now, distance is how far something moves in a given time. Okay? So if you were wearing like a pedometer, you know what one of those things are? Or, you know, that's something that you can walk and it'll tell you how far you go, you know? Or if you were in your car, you might have an odometer. So distance then is what your body actually feels. So the distance here, you go 3 meters away from the reference point. Then you stop for a second, so you've gone 0 more meters, and then you go 3 meters back towards the reference point. So you have a distance of 6 meters. All right? Now, we have to contrast that with displacement. We said displacement then is xf minus x sub I. Well, you ended up at the reference point, and you started at the reference point. So you'd have 0 minus 0, or 0 meters. So we got to be really careful. We got to be really careful with these two words. So we might say, how far did the object move? 6 meters. How far did the object move relative to the reference point? 0 meters. So how far did the object move? That's distance. How far did the object move relative to where it started? 0 meters. That's displacement. Now, that can be kind of confusing. You need to be kind of careful there. All right? Now, we just have a couple more terms here. We'll be done with this page. Okay, we have then something called trip speed versus trip. Let me get this up here. Trip speed versus trip velocity. And let me maybe scroll in a little bit here. Okay. Well, speed represents then, this trip speed represents the total distance over the total time. And the trip velocity, or also called overall velocity, would represent the total displacement divided by the total time. So for this example here, I go 6 meters, that's my total distance, in 4 seconds. Okay? So that'd be 1.5 meters per second. This is also called maybe an average. So trip velocity then would be my total displacement. So that's going to be 0 over my 4 seconds. Or I have a total trip velocity of 0 meters per second. Okay, you have to be kind of careful here. Because there's really two ways to talk about how far. We have to have two words for that, right? Distance and displacement. Okay, so we got through the next 2 pages. We're through with page 4. And I'll create another video later that has several more of the pages on. We'll talk to you later, kids. Bye.